Ladies and gentlemen, welcome to lecture 19. So today we will be talking about how to sketch the graph of a function. And also we would like to see how derivatives are involved in this procedure. Well, like I said, here we will be talking about, so today, again, it's a very, very important lecture because we will be covering the first and the second derivative tests. And you will see that we'll learn something new today. We'll learn about how derivative test is how derivatives are related to the monotonicity of a function, or how derivatives are related to concavity or of functions. So, and then at the end we will see how these new notions will help us to sketch the graph of a function. So let me get started with something with monotone functions, and let's see how these are related to derivatives. All right. Okay, so this will be the lecture today. So in other words, I named this, so using derivatives to sketch the graph of a function. All right. Well, let's start with the, I would say, the monotone function theorem. And the monotone function theorem says the following. It's pretty straightforward. Basically, it says that if I have a function, which is a differentiable function on the open interval AB, right? And something happens here. So if the first derivative is greater than 0, right? Then on the open interval AB, then the function is increasing. And we have seen what an increasing function means, right? Remember? So increasing function was that, so let me remind you. So increasing was that for x1 less than x2, this implies that f of x1 is less than f of x2. Oh my, I can barely write. Anyway. So keep this in mind. If the first derivative of a function is positive, then f is increasing. So this is how we relate the first derivative with the monotonicity of a function. And of course, here you have if if the first derivative, if f prime of x is less than 0 on AB, then f is decreasing, as you can see here, right? So this means that for x1 less than x2, and we have the other way around. So we have f of x1 is greater than f of x2, right? And let me just say one thing here. I would like to point out a remark, which is very important. I can say also, so let me just write it here. So remark. When I say increasing, I mean strictly increasing. If because right, you see here you have this strictly, you have strict inequality here. And the same way when I say decreasing, I mean strictly decreasing. We have a strict sign here. The inequality sign is strict, right? Okay. So when I say f is non-decreasing, right? Which means in a way increasing, but with the equality sign, I mean that x1 is less than x2 implies f of x1 is less or equal than f of x2, right? And when I say f is non-increasing, I mean that for x1 less than x2, this implies f of x1 is greater or equal than f of x2. So I'd like you to distinguish between the two. But anyway, what you need to know is, and also if I have there if the derivative, if f prime of x is greater or equal than 0, right? We also have equality. This means that we can say that the function is non-decreasing. So we're going to replace increasing with non-decreasing. And if f prime of x is less or equal than 0, then we say that the function is non-increasing, right? Does this make sense? Is it clear for everybody? Okay. All right, so that's what we mean. And now, since we have this monotone function theorem in our hands, then we can definitely state, again, a very important fact about derivatives and how we're going to relate this monotone function theorem to maybe some critical numbers or critical points. And the theorem is given by the following. It's called the infamous first derivative test. So let's look at it very closely. So what does the first derivative test say? It says the following. Well, suppose that I have a number c, right? That is a critical number of a function f, and this function f is defined on the open interval AB. And we have three instances here. So the first point, c f of c, is a relative maximum. Well, if, guess what? If the first derivative, if f prime of x, so if this guy here, f prime of x, so if the derivative with respect to x is greater than 0, right? For all x between a and c, right? And also f prime of x is less than 0, so this is a relative maximum, for all x between c and b. So on the left-hand side of c, the first derivative is greater than 0, and on the right side of c is the derivative is less than 0. So that's what you need to know. In other words, you know that this is what happens. It's a relative maximum. So what does it happen to the function? Can you describe this situation to me graphically? What do you mean by this? Look, I want you to translate this to me. This. Can you translate this to me? So this sentence right here. How can you translate this graphically when you look at it? So think about it. So what did we say earlier about the derivative being greater than 0? So f prime of x is greater than 0 for all x. So imagine you have an interval a, b, right? And you have a point c, which is on the graph of f, right? You have a point c of coordinates cf of c. So on the x-axis, you have the point c, which is between a and b, and you have x, right, the variable. So what happens on this portion when x is between a and c? You know that the derivative, the first derivative is greater than 0. This means that the function is what? What can you tell me in terms of the monotonicity? Nah, the derivative is positive. Yes, I agree. But what can you tell me about the monotonicity of a function, of the function? What did we say earlier? Look here. What did we say? What did the monotone function theorem say? I'm all ears and eyes. I can't hear or see. What did we say? So we said that if the first derivative is positive, then the function increases, right? It goes up. And if the first derivative is negative, then the function goes down. So if you look here, okay, translate this to me graphically. What do you mean? So the first derivative is positive, which means that the function is what? Is what? Increasing, decreasing, how is it? Increasing, exactly. So the function goes up all the way up to that point. So you see, you have something like this. Look, let me draw a picture. It goes up here, you have a max, goes down. See, this is a relative maximum. Let's say here we have C, and this is the point C f of C. Let's just say here we have A, and here we have B. Let's say we have like this, B, right? You see the function is increasing on this portion all the way up here, then it goes down here, it's decreasing, as you can see. The first derivative is up, is positive, then it reaches up to a maximum, then it goes down. So this is how you should think of this. You should have this image in mind. All right, so this is what relative maximum, the relative maximum is about. Now let's see a relative min. How would you describe this? So the definition says the following. So a point of coordinate C, f of C is a relative minimum if f prime of x is strictly less than 0. So f prime here of x is less than 0, right? For all x between A and C, and f prime of x is greater than 0 for on this portion when x is between C and B. What can you tell me? How would you describe this graphically? So let's see, if we look on the portion between, it will be decreasing where and where? Okay, be more specific, Brian. Between A and C, it will be what? It will be decreasing, right? And between C and B, it will be what? Let me see. Increasing, exactly, correct. So we will have something like this. Let me just erase this. So we will have something, let's say, so this will be decreasing. It goes here, right? Let's say here, and then it will be like this, let's say. And this will be the point of coordinate C, f of C. As you can see on this portion right here, it's decreasing. This will be a relative minimum, and then it goes up, it's increasing again. So that's the second situation. But now we also have a third situation. So you see, in the first two situations, when we have a relative maximum and a relative minimum, we're dealing with an extremum point, right? But there is also a third situation when we will not be dealing with an extremum point. So in this situation, we will say the following. So we will say that the point CF of C is not an extremum if, and pay attention here, if f prime of x has the same sign for all x between A and C, and also between x, C, and B. So for example, you can have the following. You can have something like this, look. Let me draw the graph of this, look. It goes down, you don't have an extremum point. It goes from negative infinity to positive infinity. So the derivative in this case will depend on how you look at it. It goes up, right? So anyway, or it goes down, right? So the derivative has the same sign. That's what we mean for all x between A and C, and also C and B. So that's the first derivative test. And we would like to see some examples. How do we apply the first derivative test on a specific situation? So I'd like you to look again at this. And now let's see an example. And I would like you to work on this, on the following example. So this is the question where we would like to address. So the following example says the following. So we consider the following function. It's a cubic, right? So f of x is x cubed minus 3x squared minus 9x plus 1. And we are interested in dealing with the following two questions. The first one, where is f of x increasing or decreasing? And the second one, we would like to find any relative extrema. So I would like you to think of this problem for a bit. Let's see, for a couple of minutes. So what do you think? So what do we need to do first? Exactly. So we'd like to, and also derivative, and what else? You take the derivative and what? What should we do with it? Exactly, and set it equal to 0. So to work with the first question, right, to see where the function is increasing or decreasing, we would like to take the first derivative. So the idea is to take the first derivative, right, and set it equal to 0. So that's what you need to do. All right, that's great. So let's do that. So let's compute the derivative. So what's the derivative of f? So f prime, well, if you compute it using the sum rule and also the power rule, whatever, at this point, I believe that all of you, I hope, know how to compute derivatives of functions. So the derivative will be given by this. So f prime of x is 3x squared minus 6x minus 9, right? So that's the derivative. And what we're going to do right now is we're gonna set this equal to 0, just like we said, and we will have to solve this equation. So this is a quadratic equation that we need to solve. But that's great. Well, because we can factor this one out. So we can factor first we can take a 3 out, right? So this guy, we can write this as, let me write it, 3 times x squared minus 2x minus 3 equals 0. So since 3 is different than 0, then this guy is 0. And we can also factor this guy as well, and we can factor it in this way. So x squared minus 2x minus 3 is nothing else than just x plus 1 times x minus 3. And now we need to solve this equation, and I believe that the situation is pretty clear at this point. So what solutions do we have for this equation, for this last equation, this one here? What are the solutions for this? X equals -1 and x equals 3. As you can see them here. So these are the solutions for this equation. Exactly. Ooh. Great. So what are the extreme up for these functions? Are -1 and 3. And we'd like to see. Wait, what did you write? Yeah, I know you meant -1, 3. It's fine. All right. And now we would like to see. So we should draw a chart here. So we will see on what happens on the interval -∞, -1, then on the interval -1, 3, and then from 3 to infinity. So we would like to see what happens with the derivative of a function on the interval -∞, -1. And what can you tell me? Right? What can you tell me about this? What do you think? The derivative is what? Positive, negative? Because 0 is not. 0 will be only at these 2 points, -1 and 3. But I'm interested what happens from -∞ all the way up to -1. Is the derivative positive or negative? For example, plug, let's see, the derivative, f prime is this, right? So plug -2 is negative. Okay, so you say it's negative for all x. Let me take f prime of 2. So it will be 3 times 2 squared minus 3 times 2 minus 9. This will be 12 minus, what did I do here? Wait a second. Okay. 6 times 2 minus 9. So it's 12 minus 9. Is this the... So it's negative, right? Okay. So this means that this is -9, which is negative. All right. And you can do the same thing for the others, right? What if we plug in... let's see, what about between -1 and -3? What if we plug in, let's say, 0? F of 0 is what? Is negative, right? So let's see. And I think there is a mistake here. The derivative is negative here, sorry. So f prime is less than 0. Well, there is a mistake in this. Anyway. And now let's see what happens on the interval. Let's see f prime of 4. So when we plug in f prime of 4, what do we have? So we have 3 times 4 squared minus 6 times 4 minus 9. So how is this? So this is 48 minus 24 minus 9. Well, definitely this is positive. So indeed this is correct here. So this is plus here. This is minus here. All right. And now what can you tell me? On what interval is my function increasing? Let's see. Sabrina says on increasing, I said. No, because there is a mistake in the slide. So this is negative here. So increasing, it's only this here. So increasing will be only on this. So on 3 infinity. Exactly, on 3 infinity. And decreasing will be on what? On negative infinity 1. Right, so this is negative infinity 3, sorry. There is a mistake here in the slide, so let me see. So so f prime of negative, let's see. There is a question. In your original equation, that will give you no. You only want to see where the derivative is positive or negative, not the original equation. So for example, let's actually compute it. If f maybe, so f prime, let me say, let me take -2, f prime of -2. Because maybe I did something, maybe it's correct what I know. So f prime of -2 is 3 times -2 squared minus 6 times -2 minus 9. Maybe it is positive, and I was, maybe it was correct the first time that I did it. So this would be 12 plus, actually it is positive, I was wrong. So 12 plus, this is plus 12 minus 9, okay. Sorry about that, this is wrong here. So that's correct. So everything is correct. So this is positive. So, oh, what am I? Minus 9, which is positive, right? So indeed, the function is correct. Sorry about that. So if you want to see where the function is increasing, you look at this and this, right? The derivative is positive. So you take the union of these two intervals, so negative infinity, -1, and then 3 positive infinity, so which you'll find here. And then decreasing will be on negative, it's decreasing will be right here, right on this portion here. So on this portion here, it's negative. So on this portion, the function will be, the derivative is negative, so the function will be decreasing, which you find it here. All right, and now we would like to see any relative extrema. So when we see any relative extrema, so what do you think? What are the relative extrema? You see, the function is increasing. If you imagine the graph of f, right? So it goes, it's increasing, right? So it goes up, right, up to some point where we, of course, is -1 and it's something. Well, we'll see what that is. So we have to evaluate, and I think Mohammed was saying something, we input the values on the first, but yeah, but only for the extreme value. So we would like to compute f of -1 and f of 3. So f of -1 is what? Let's see. You mean at those 2 points, critical points? Brian? So, yeah, exactly. Yes, you're right. Yes. Yes, it will be, yes, exactly. All right, so the function is increasing, goes up all the way. So let's compute f of -1 first. So f of -1, it's, okay, it's 6. And f of 3, whatever, it's -26. You'll check this as an exercise. So what the function does, if you look at the graph, if you want to imagine the graph of f, so it goes from -infinity all the way to this point, of course, -1 and 6. Then it goes down on the interval -1 and 3. It goes down, is decreasing, right? Right, all the way to the point of coordinates 3 and -26, and then it goes up from values greater than 3 to infinity. So that's how you imagine the graph of that, right? And then you can say, since it's increasing and it reaches all the way to that point, and then it goes down, that will be the relative maximum. So that point which is of coordinates. Look at this one here. So this one will be a relative max, and this guy will be a relative min. So relative max, it's increasing, goes up to that point, and it goes down to that point, and then it goes up. So it's a max and a min, and they're relative, right? Okay, let's see, any questions? Is it clear now? Anyway, we'll deal with more of these examples. And by the way, pay attention. You should expect problems like this on the final exam. You can bet on it, right? Right? Okay. Now let's move to something else. Well, we have talked about how to relate the monotonicity and the derivative. Now I would like to relate the concavity and the derivative. And in fact, we'll be talking about the relationship between the concavity of a function and the second derivative. So let's look at this one. So the concavity of a function, like I said, it will involve the second derivative. But first, let's see what does it mean for a function to be concave. And in fact, we'll be talking about concave up, concave down. In other words, concave up, please imagine this picture. The graph holds the water, right? It's like this. And concave down, it doesn't hold the water. It's like this. So if the graph of f lies above all its tangents on an interval, right? So if we have a function f which is defined on an interval I, and if the graph of f lies above all of its tangents, then we say to be this function to be concave up. So this is what you need to remember. It lies above all its tangents. So graphically, geometrically, this is what it means. So we say this that f is concave up on that interval. And of course, the other situation, if the graph of f lies below all of its tangents, so this word below, right, on the interval I, so lies below, then the function is said to be concave down on the interval I. And as you can see here, there is a picture to illustrate this. And you see, this function is to be concave up. The tangent, okay, so you see all of its tangent lies above. You see, you have this and below. Oops. So this is graphically, this is the situation. Look at this tangents, right? Okay, and now we would like to see how is this related to derivatives, right? And in this way, we will see a characterization, which is the following. So I would like to draw your attention with this fact here. You see, if the second derivative of a function is positive on the interval a, b, then f is concave up on that interval. If the second derivative of the function at any point, so this is at any point, is negative, then f is concave down. So that's what we mean concave up, concave down. Well, sometimes we call concave up to be convex, so convexity. But I don't know, the Calc 1 manuals, they want to use this with concave up, concave down. Anyway, it doesn't matter. If at some point you will see the notion of convexity or a function to be convex, please keep in mind that that will refer to concave up. So we usually say a function is convex if the second derivative is positive, it's concave if the second derivative is negative. In fact, let me tell you a historical fact. People didn't even know this convexity thing, concavity, convexity thing, came out in mathematical literature very late, in 1906. And it's such a natural notion that now we even do it in calculus 1, because you see there is this relationship between the concavity and derivatives. And in fact, it's related to the second derivative. So that's the derivative characterization of concavity, right? Again, the second derivative is positive, the function is concave up. The second derivative is negative, the function is concave down. So that's what you need to know. Well, and also we would like to see, since we talked about, so let me tell you about this parallel. So we have the first derivative, and we have seen what it means for a function to have a relative extrema, so a relative min, a relative max. And we have seen that that's an extremum point. But we would like to see what happened if, so we saw that the extremum point is that point where the function changes its monotonicity. So it becomes from increasing, it becomes decreasing, or the other way around. But we would like to see if something like this happens to the second derivative. And in fact, we will call this point, so we will be talking about such a point is called an inflection point. So a point P of coordinates C and F of C is called an inflection point, right? So this is called an inflection point if the graph changes its concavity at the point C. This is very important here. So if the graph changes its concavity at the point C. Right? So keep this in mind. Once again, a point P of coordinates C and F of C, it's called an inflection point if the graph changes its concavity at C. Also, note that if F of C is not defined, then this point P of coordinates C, F of C cannot be an inflection point. So this is important. And let me say this again. If F of C is not defined, then this point cannot be an inflection point. Exactly, great, exactly. Well, you said it before I wanted to say, so you anticipated my next slide. So with this regard, we will have a similar situation. So we will deal now with the second derivative test. And again, this will be important, very important, because it will give you also information about a relative maximum and relative minimum. It will tell you exactly what happens. So let's read it. So suppose that a point C is a critical number of function f, which is, and the function f is defined on an open interval a b, right? If f prime of x is less than 0, then guess what? This point of coordinates C and F of C is a relative maximum. Once again, if the second, this time it will involve the second derivative, not the first derivative. So I'd like you to distinguish between them. But anyway, we'll talk, I'll go back to the first derivative test and we'll see how we compare the two tests. So again, if at the second derivative of f is 0, then this point of coordinates c, f of c is a relative maximum. If f second prime of x is positive, then the point of coordinates c, f of c is a relative minimum. And let's see what happens when the derivative when the second derivative is 0. Well, unfortunately, we're not successful here. The second derivative of x is, if the second derivative of x is 0, then this test will fail. And also, we cannot say exactly what happens to this point of coordinates c, f of c. Well, it may be a relative max, a relative min, or neither of them. So we should try another approach. So now let me go back to the first derivative test. So, and let's compare the two. Look, the first derivative test, it will give you some information about the first derivative. So the first derivative will give you an information about the relative maximum or relative minimum. And also, not just that, but also, okay, some similarities between the two tests. So the first and the second derivative test will give you precise information about how to find a relative max or a relative min, or how not to find, how to say that a function has neither of those. And also, what we can distinguish between the two is that the first derivative test will give you precise information on the intervals of monotonicity of the function f. So keep that in mind. While the second derivative test will give you also information about the relative min or a relative max. Let me go back to it. A relative min or relative max, right? In terms of the second derivative, or neither of them. But also it will give you something something different than what the first derivative test will give you. So it will give you the second derivative test gives you information about the intervals of concavity, or intervals of concavity. So you will say, well, on what interval is my function concave up, concave down, and so on. Right? All right, so in the remaining time, I would like to go back to that example, right? You see, we talked about this example. So we consider this function, and we apply the first derivative test here. So that's what we did. So we applied the first derivative test. But now I would like to consider the same example, and I'd like to see maybe I'd like to find the intervals of concavity and convexity. So let me consider the same example. And I would like to ask you, look, and also I'm going to give you the graph. So again, we consider this function. So we'll deal with a couple of examples in the remaining time. So we have the same function, the cubic function, x cubed minus 3x squared minus 9x plus 1. And now I'm going to ask you something different. So I'm going to ask you where the function f is concave up or down, find the inflection points, and also graph it. Well, the graph is already given. Well, I shouldn't have said it, but anyway, that's the graph of the function. But you can actually say by just looking at the graph, right? Look, it goes like this, all the way up to this point, and it goes here. goes here, goes up. All right, I want you to think of this problem, and by just looking at the graph of f, can you tell me some informations? So we have already seen what the relative max and relative mins are from previous considerations, as you can see here and here. So the one above is the relative max, the one below is the relative min. But also something happens at that point, 1 and negative 10. Okay, so think about it for a couple of minutes. So how would you relate when we're asked this question, where is the function f concave up or down? So how would you relate this? You relate it to what? The function where the function f is concave up or down. To what? To the second derivative, right? If we go back, look. The second derivative test will give you that, right? In fact, look here, the definition. The derivative characterization of concavity will give you that, right? So let's see this. Oh, so let's see. So let's compute the first derivative and second derivative. We have already computed the first derivative. And now it's this first derivative is given by 3x squared minus 6x minus 9. No problem. We're going to take the derivative one more time. The second derivative is given by 6x minus 6. And now if we would like to find the inflection point, and we'll also like to see what the intervals of concavity or convexity, we will see, we're going to set this equal to 0. So we're going to solve the equation f second prime of x equals 0, right? So we're going to get x equals 1. So that would be the inflection point. Ooch. Great. And now we're going to evaluate f of 1. So f of 1 is negative 10, sorry. Right, so we have this. So we'll have this inflection point right here of coordinates 1 and negative 10. So this will be what we will call the inflection point. So the inflection point, just like we previously said, inflection point, just one. Inflection point, just like we said previously, look here, is the point where the graph of f changes its concavity. So if it changes from concave up to concave down or the other way around, right? Okay, so now let me, and also, so this is the inflection point. So the inflection point will be this point of coordinates 1 and negative 10. Also, let me recall the fact that the function we have previously seen that the function is increasing on the interval negative infinity, negative 1, united with the interval 3, positive infinity, and also is decreasing on the open interval negative 1 and 3. All right. Now, if I ask you, giving all this information, can you tell me on which interval the function is concave up and concave down? I want to hear it. And also by just looking at the graph. Come on, tell me. Well, I cannot hear you. So what interval do you think? -10? Look, it's right here. You see, it's written. So we got -10 from f of 1. So by evaluating f of x at x equals 1, look here. Is it clear now? So let's see. On what interval is my function concave up and on what interval is concave down? So let's see. -infinity all the way to, yes, exactly, on the interval. Let me see. 1, exactly, Zach. So the function will be concave up, concave up or concave down? So how do you think the derivative will be like? So it will be, so concave down, exactly. So it will be concave down. So if you look at the graph of this, look, let me see. Concave down will be from here all the way to here. So here is concave down. And now from here, let me draw with another color. From here to here, it goes. So this will be concave up. Great. So again, in fact, we can just plug in some numbers for the second derivative and you'll see which one is positive, which one is negative. So, right. So for example, for concave down, so f second prime of 0, let's say. So here we can plug in f second prime of 0. This will be is -6, which is negative. So, right. And in this case, we can plug in f second prime of, let's say 2. And it will give you 12 minus 6, which is 6, which is positive. So there you go. Right. So we know at this point by just looking at the graph, and if you look at it, we know that the function is concave down, but it's increasing. That's the thing. It's increasing all the way up to the point -1 and 6. So you see, you can answer. You will have a question like this on the final exam. 100% sure, guaranteed. A question like this will be on the final exam. So you better pay attention to what I say here. And also, since I'm recording the video, you better look at the video very closely. So again, by looking at derivatives, you can, the first derivative will give you information about relative min and relative max. Also, the second derivative will give you information about that as well. But also, the first derivative gives you information about the monotonicity of a function. So in other words, it will tell you where the function is increasing or decreasing. And the second derivative will give you information about the concavity of the function, right? It will tell you where the function is concave up or concave down, as you have seen in this example. And now let's, well, I want to do another one. So I'd like you to, look, this is an exam type problem. So a final exam type problem would look like this. So we consider this function f of x to be x to the 4th minus 4x cubed. So we would like to see where the function f is increasing or decreasing. We would like to find out any relative extrema. Then we would like to find where the function f is concave up or concave down. And then we would like to find any inflection points. And then at the end, we would like to graph the function. So the graph will be like this. So what would you do in the first place? So we need to answer the first question. So how would you answer the first question? What would you do? So how would you find information about the monotonicity of a function? What will give you that? But even before that, we need to do what? Well, I cannot hear you. Do the derivative test. Which one? The first derivative test, right? So in order for us to find information about if the function is increasing or decreasing, we need to apply the first derivative test. But before we apply the derivative test, we need to compute the first derivative, right? So the first, and set it equal to 0 to find the extremum point, right? Extrema. So the first derivative was not hard to see that the first derivative f prime of x is nothing else than just 4x cubed minus 12x squared. And this will be nothing else than just 4x squared. And you can factor here times x minus 3. So this equation, if you look at it, right? If you look at this equation here, we'll have two solutions, right? It's just the product of two functions is 0, so this means that either one of them is 0. In other words, 4x squared is 0 or x minus 3 is 0. So this implies that x is 0 or x is 3. So let's see. So these are the extreme points right here, x equals 0 and 3. And now we'd like to see on what interval is the function increasing and on what interval is the function decreasing. All right, great. So let's look on, let me draw the picture here so that it looks clearer. You can also draw it like this. So let's say here is infinity, here is negative infinity, here we have 0, here we have 3. So we know these 2 points, these are the extremum points for our function. And we'd like to see what happens on this portion from negative infinity to 0. So let's plug in f prime x equals -1 for f prime. So on this portion, in fact, you can actually see, but you can plug in, let's see, f of -1 is what? If 4 times 1 minus 3. And this is 4 times -2, which is -8, and this is negative. So you'll put on this portion here, you'll put negative here, right? And now let's see between 0 and 3 what happens. So let's take a value, let's plug in a value, let's say f of 1. So f of 1. F of 1 is what? Is 4 times 1 minus 3. So it's wait. 1 minus 3, yes. Wait, I think I made a mistake here. This is -1 here. Anyway, it's still negative, so it's -16 here. Oh my algebra is, it is what it is. So here is -8. So again, is negative. Ooch. So again, here on this portion will be negative. And now let's see what happens on the interval 3 infinity. So on the interval of 3 infinity, let's plug in f of 4, let's say. F of 4 for the derivative will be what? 4 times 4 squared, 4 times 16 times 4 minus 3, which is 1. And anyway, this is positive, I don't care, so this will be positive here. Just like you can see on this chart. And now, you can also look on this chart. So on the interval negative infinity 0, the first derivative is negative. Also on the interval 0, 3, the first derivative is negative, but also starting for 3, infinity, the derivative will be positive. So in other words, this means that the function is increasing on the interval 3, infinity, right? And decreasing on negative infinity 3. And x equals 3 is a relative extremum. It's an extremum point. And now we'd like to see which one is a relative min, which one is a relative max. So we would like to compute f of 0 and f of 3. F of 0 is nothing else than 0, and f of 3, if you plug it in, it will give you okay, so it'll be negative 27. Great. So you see the point at x equals 0, 0, because it will give you the function 0. It's just a fixed point, is not the relative extremum, right? So this is not the relative extremum. But now at x equals 3, the point will be a relative min, since we know that the function is decreasing. All right, great. So we have seen this, this. And now we would like to see where the function is concave up, is concave down. To find this, what do we need to do? So what do we need to do to find this? We need the second derivative, right? So we compute exactly, we need to take the second derivative. So now we're going to take the second derivative, and the second derivative would look like this, right? So the second derivative is the first derivative, is the derivative of the first derivative. So it will give you this. Just a computation will give you this. Anyway, I'll leave the computations to you. I'm sure you can do it. And now to find the inflection points, we need to set this equal to 0. So this equation will have solutions x equals 0 or x equals 2, right? Well, and we need to decide which one is which one. So we need to decide on what happens when, what interval is the function concave up or concave down. So we know the inflection points are 0 and 2. And now we're going to do the same thing, the exact same thing we're going to do. So we like to see on the interval negative infinity 0, then on the interval 0, 2, and then on the interval 2 infinity. So let's see, the second derivative. Let's plug in a second derivative at negative 1 is what? At negative 1, it will be 12 times negative 1 times negative 1, negative 3. Let's see, is it positive? So this will be negative, anyway, it's positive. So the second derivative, as you can see here, is positive. All right, so the function is concave up. And also, let's see what happens in between. So again, let's plug in a number. So f prime of between 0 and 2, let's say of 1. So it's 12 times 1 minus, times 1 minus 2. So this is negative. Ouch, sorry about that. This is negative here. Okay. So the function is the second derivative on the interval 0, 2 is negative. Great. Now let's see on the interval 2, infinity. Let's plug in 3. So f second prime of 3 will be what? Will be, let's look at the second derivative. So it will be 12 times 3 times 3 minus 2. This will be positive. I don't even care how much is it. So it will be positive here. Great. And now I can say the intervals of concavity. As you can see on the interval negative infinity 0, the second derivative is positive, which means that the function is concave up. Then in between 0 and 2, the second derivative is negative, which means that the function is concave down. And then on the interval to infinity, the second derivative is positive, which means that the function is concave up. And that's what we have right here. Right, you see it? Boom. That's it, right here. So the inflection points, so we have the inflection number, let's call them. And the inflection point, we just have to plug in. So we have these numbers, 0 and 3, 0 and 2, sorry, look at them here. And we'd like to plug in for the function f these 2 points. In fact, let me write them with red. So we'd like to plug f of 0 to compute f of 0 and f of 2. So f of 0 is what? Is 0, right? And f of 2, if we look at the function, is 2 to the 4th minus 4 times 2 cubed, which will give you 16 minus 32, which is negative 16. And you'll get these 2 points right here. See, of coordinates 0, 0, and 2, and negative 16. Well, and now we found where the function f is concave down, concave up. We found the inflection points, and now the only thing we need to do is just to graph the function. And we can graph it. And if you look at the graph of f, you see it goes like this. It's decreasing, right? And it has this point, this inflection point right here, right? And keep in mind that it's decreasing all the way to 3. So it keeps going, still decreasing even here, all the way here, up to this point here. But as you can see, the function will start from 2 to be concave up. From here, it will be concave up. And then it will be increasing from 3 all the way to infinity. It keeps going like this, right? Right? And by looking at this graph, you will see some points. You will see the point 0, 0, which is neither extreme, so it's kind of flat, so you don't see exactly what it is. But you can also see that the point 2 and negative 16 will be an inflection point. Also, 0, 0 will be an inflection point, so these are the 2 inflection points, right? And also we will see that, so 0, 0 will be an inflection point, but it will not be a relative extremum. That's the thing. And now we will see that the concavity, so it's the concave up from negative infinity all the way to 0, and then it will start from 2. So let me draw another color here. So you see, this is concave up. You see it here, like this, all the way from here, and then it will start to be from the point of course from here all the way up. So this on this portion right here is concave up, and then concave down will be between 0 and 2. So this is what it means to be a function concave down here. And also, if you look, it will have a relative min, which is this point. The lowest point on the graph, which is given by this guy here, is the relative min. So you see, having all this information will help you to draw the graph of that. Anyway, I had other examples, but I would like to discuss them next time, because I don't want to, this is a very important stuff. And I think I will stop here with the lecture. Well, if you have any questions, I'd like you to pay attention to these things that we're discussing, because this will be very important. And next time I will continue with more examples of this type. In fact, I'll consider 2 more examples where we apply the first and the second derivative tests. And we'll continue with some other stuff as well. Anyway, I think I'm going to stop here. Please feel free to stop by at my office hours in 10 minutes. The link is different, by the way, for office hours. Okay, I'll see you. Take care. Bye-bye.